As we begin continuing with similar items or similarity, we're going to talk about similar figures, and in doing so, we talk about figures, not necessarily triangles, but any form of polygon. And we want to remember that a similar polygon is nothing more than two or more polygons in which the corresponding angles are congruent, and then the lengths of the corresponding sides are in proportion. And that has to do directly with that dilation, a transformation in which each point of the image lies on the same line as the corresponding point of the pre-image, and then we have that center of dilation, um, and that center of dilation is that fixed point, you know, from each the image and the pre-image, where we have our corresponding angles and proportional sides. So just keeping that in mind as we were talking about similarity, these dilations, we want to remember that uh, the lengths of the sides are proportional by a scale factor, and that's but we maintain the same angle. And so in doing so, we're going to discuss, or we want to be able to verify the properties of, goodness, spell check gets me every time, properties of dilations, including the scale factor and the slopes of the corresponding line segments, and determine if two polygons are similar by using dilations. Find the coordinates of the vertices of an image or pre-image. So again, we were wanting to be able to move forward and back via image or pre-image and find out where it originated from, or where we are dilating to. And in addition to being able to find that new location as we work on the coordinate plane, we want to be able to use the distance formula. So we have to remember that um, when I'm trying to figure out a dilation, or this center, how something has changed, and my image goes from right here to right here, um, and this distance that I'm going to be going, here was one value, and then I get to this other value, that is going to be my vertices, maintaining that from the origin of dilation. And what I'm going to be using is the distance formula. And I'm able to use the distance formula because that allows me to determine lengths on the coordinate plane. So I can use the value, the xy value here, and then I have a new xy value. So I can find out, and using, of course, in this case, the origin, would be able to use the distance formula to find out how long, is this dilation. So that's why we're going to be using the distance formula. And of course, that should take you back to the 8th grade. And if it doesn't, just remember that this is derived from the use of Pythagorean's theorem. Pythagoras was a wonderful man who came up, who put his name on a great theorem that has been useful over the centuries. So using the distance formula can be used to find the distance between 2 points on the coordinate plane. So if I look here and I've identified these 2 points as A and B on my coordinate plane, I hope that you can see that A, when you read this, is going to be the x value, its coordinate is going to be 1, 2, and then my B value, my B coordinate, is going to be x is 2 and y is 4. So now I'm able to take and use these to figure out the distance between point A and point B. And in doing so, of course, we are going to use the distance formula, and distance is going to equal. All right, so we have x2. So we're looking for x2, and we'll just say I'm going to say that this is x2, y2, this will be x1, y1. It will work out no matter how you do it, whichever point you choose is 1 and 2. So my x2 is 2 minus 1, because that's my x1 squared, plus y2 is going to be 4, and not comma, but minus, my y1 is 2 squared, and that's going to equal, my distance is going to be the square root of 1 squared plus 2 squared, which is going to be the square root of 1 plus 4, or which is the square root of 5. So the distance between point A and point B is going to be the square root of 5, and that's using the distance formula. How do I use it? That's how I use it. So this distance between right here, that is going to be the square root of 5. Plugging the values in and simply, well, simplifying using the distance formula. And if you took a moment and you wanted to find out what is the distance, if you wanted to find out the distance between point B and point C, stop the video and give it a chance, or plug it in on your own and then check your answers. And I will give you the answer here, but go ahead and stop it, see if you can figure it out. And there's your answer, of course. Distance would have been 5, and that's the information that you would have plugged in. And just check your work against that, and we'll see how you're able to do it. If not, well, we can go ahead and answer those questions. So the distance between B and C was 5. Okay, as we start using dilations, now the dilation, again, is, if you recall, it's going to be a dilation. 0 would be from the origin, and it is going to be by 0.5, and it is going to involve my xy coordinates. So if I look at this in my new diagram, basically everything is going to be 0.5. So that's going to be 0.5x and 0.5y. That is going to be the change. So this is actually easy from the origin in a sense that I could plug in the q. Q is going to be 0.02 is the coordinate for q. Well, 1/2 of 0 is going to remain 0, right? So I have 0.5 times 0, which is 0, and then I have 0.5 times 2, which is going to be 1. So the new coordinate of q, the transformed q, is going to be 0, 1. So q is going to be transformed to right here. That is q1. So everything is going to be cut in half. This is going to be, I'm sorry, not 1. Q prime, R prime, S prime, and T prime. So my new dilated image is going to be right here. It is going to be dilated at a scale factor of 0.5, and there is my new image about the origin. Now, if we do the same, if we do the same form of dilation, but here in this next example, what I've done is I've changed my center of dilation to Q. So here is my center of dilation. So my x coordinates and my y coordinates are still going to be half based on Q. And in this case, I'm just going to show you S, right? And S is easy to come up with. And we're going to end up moving it halfway. The distance is going to be in half. I'm not going to do the distance formula here, but I know that if the distance from Q is 1, 2, 3, 4, 5, then my new distance is going to be 2.5, which is 1, 2, and a half. So my new point for Q, or for S, that is my new location for my S, which is still going to be, my x value is still going to be 0, and my y value is actually going to be negative 0.5. So I was just changing the center of dilation. And then, of course, the same would go for this other example where my center of dilation is going to be the T. So T, when I go to do my new my new dilation, R. If we look at R is currently negative 4, 0. Well, my new translation of R, or my new dilation, is going to be R is going to be 1/2. So 1/2 the distance. Well, the distance is actually, to look at it, is going to be 1, 2, 3, 4, 5, 6, 7, 8, right? 8. So it's going to be half that distance. So R, the new R prime is actually going to be 0, 0. as the new coordinate. So just looking at those transformations, the dilations, and how they would work on the coordinate plane, and we'll get into more detail here in the next couple of slides. All right, so here we are given triangle ABC. So we have triangle ABC, and we want to use the dilation, and the center is going to be from the origin. Okay, the center of dilation will be from the origin, and we want to create a similar triangle with side lengths that are 3 times as large. So 3 times as large means that we're going to be multiplying by 3. So as we write that, that may appear to be something along of dilation. The center is the origin, and we want a scale factor of 3 times. And that is going to be our xy values, and let's just see what we get. So if we start off with A is currently -1, 2. And that new translation, A prime, is going to be -1 times, sorry, I got a little bit ahead of myself there, -1 times 3, because that's my scale factor. And Y is going to be 2 times 3. So that is going to be A prime is going to be -3, 6. So let's see here, that is going to be -1, 2, 3, and 2, 3, 4, 5, 6. -6. My bad, I never put the scales on there. So this is going to be my new A prime. And let's see here, B is currently -1, -1, and if B prime is going to be by a scale factor of 3 also. So we have -1 times 3 and -1 times 3. And so my B prime is going to be -3, -3. So that is going to bring me right about here. It looks like I made a mistake on my A prime, right? I didn't go over 3. There we go. And then C, my C value. C is currently going to be, X is 2, Y is -1, and our new C transformation dilation is going to be 2 times 3, and the Y is going to be -1 times 3. Times 3. So let's see here, that is going to be then C prime is going to be 6, -3. So we are looking at 5, 6, -3 right there. And if I fill that in, or not fill that in, but connect my lines, here we got C, B, and you'll notice some of the properties or some of the characteristics that, if you'll notice, my corresponding sides are going to be parallel, right? AB is parallel to A prime, B prime. BC is parallel to, B prime, C prime. And then, of course, my angles are preserved here. These are going to be constant angles. So that is just sort of using my dilation rules to find out my new points. You know, in looking at this image, if we didn't know any of the math, right? If we only see the image, are we able to come up with the dilation? And I would hope that what you can do is you can look at this original image, my pre-image, and I could say that my pre-image, BC, right? The length of BC was 1, 2, 3. Well, the length of the dilation, B prime, C prime, is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. I would hope that you can see that we have gone from, BC has been moved to B prime, C prime from 3 to 9, and I would hope that you can look at that and say, well, that's 3 times greater, so the scale factor is going to give me a 3. So I'm looking at a scale factor of 3. So when I go to write that, I should know that, hey, somewhere along the lines, wherever I have, my center of dilation, I may not know what it is, but I do know that the scale factor is 3. And then we can work with that. just remember, as we are working with similar figures can be created using dilations, because dilations preserve the angle measure and create a proportional relationship in the length measurements. And remembering that this dilation, from some point in the scale factor of n, as I move something on the coordinate plane, that is going to, that scale factor, I am going to multiply my new values, right? I'm going to multiply my x value by the scale factor to find my new x value. I'm going to multiply the scale factor times the y value to find my new y value. And each side of this similar figure is multiplied by that same scale of n. So the segments, in similar figures have the same slope after the dilation. And the center of dilation does not always have to be the origin here. Yes, it is the origin, but it could just be a point. It could be a different location on the coordinate plane. So just keep that in mind when we're working with this and looking at the orientation of the images.